The temperatures are plotted on the y-axis and the time in minutes on x-axis. The graph is shown in figure. The graph shows that initially both the temperatures T1 and T2 are identical. However, as time passes, temperature T1 of water in the lower part of the cylinder decreases fast, while temperature T2 of water in the upper part of the cylinder decreases comparatively slowly. However, once the temperature T1 of the lower part reaches 4 degrees Celsius, it remains almost stable at that temperature. T2 decreases slowly to 4 degrees Celsius. Thereafter, since T2 starts changing rapidly, it records 0 degrees Celsius first, and after that, the lower thermometer T1 records 0 degrees Celsius temperature. The point of intersection of the two curves shows the temperature of maximum density. How can we explain these observations? Initially, the temperature of the water in the middle of the cylinder lowers due to freezing mixture in the outer bowl. Since the temperature of the water there decreases, its volume decreases and its density increases. The water with higher density moves downwards. Therefore, the lower thermometer T1 shows rapid fall in temperature, and this continues till the temperature of water becomes equal to 4 degrees Celsius. When the temperature of water starts decreasing below 4 degrees Celsius, its volume increases and the density decreases. It therefore moves in the upward direction. The temperature of water in upper part, that is T2, therefore decreases rapidly to 0 degrees Celsius. The temperature of water in the lower part, that is T1, however, remains at 4 degrees Celsius for some time and then decreases slowly to 0 degrees Celsius. The anomalous behavior of water plays an important role in the survival of aquatic plants and animals in cold regions. In cold countries, the temperature of the atmosphere may fall to 0 degree in winter. The water at the surface of the pond and the lake begins to contract as a result. The volume decreases and the density of water on the surface increases, which then begins to sink to the bottom. This process continues till the temperature of all the water in the lake falls to 4 degrees Celsius. That is, it begins to expand instead of contracting. Consequently, its density decreases so that it remains on the surface. The temperature of the water at the surface goes on decreasing to 0 degrees Celsius, and finally the water gets converted into ice. Water below the ice continues to remain at 4 degrees. Thus, at 4 degrees Celsius, fishes, aquatic animals and plants are survived. In winters, sometimes the pipelines carrying the water burst. When the temperature of the atmosphere falls below 4 degrees Celsius, water in the pipes begins to expand. At 0 degrees, it turns into ice. That creates pressure in the pipes and the pipelines burst. Crumbling of rock into pieces. Water enters into the narrow cracks of rock. When the temperatures of the surroundings falls below 4 degrees, the water begins to expand. As there is no place in the narrow crack for expansion of water, thus tremendous pressure is exerted on the rock and it breaks into pieces. Dew point and humidity. 71% of Earth's surface is covered with water, and evaporation of water takes place continuously. Hence, the atmosphere always contains some quantity of water vapor. Illustrations. Number 1. When we enter in a warm room after being outside on a cold early morning, spectacles steam up. Because the temperature of the outside air is below a particular temperature of the air in the room, also called the dew point, therefore the water vapor condenses upon the glass. Number 2. A cold drink bottle taken out of refrigerator. We observe that the water condenses on the bottle. The amount of water vapor present in the atmosphere determines the nature of the weather. A given volume of air can contain maximum amount of water vapor at particular temperature and is said to be the saturated water vapor with that temperature. The quantity of water vapor required to saturate the air depends on the temperature. If air contains a quantity of water vapor less than the maximum quantity of the water vapor it can hold, the air is said to be unsaturated with the water vapor. Dew point. When the sample of air is cooled sufficiently, the water vapor present in it gets saturated. Some water condenses into water droplets. The temperature at which the air becomes saturated with water vapor is called the dew point. Humidity. The dampness or moisture in air due to water vapor content is called humidity. Absolute humidity. The percent of water vapor present in the air, if measured in terms of quantity, is called absolute humidity. The mass of water vapor per unit volume of air is called absolute humidity. Dry air. If the quantity of water vapor present in the air is very small compared to the quantity required to saturate air, we feel that the air is dry. Moist air. If the quantity of water vapor present in the air is little less than the quantity required to saturate the air, we feel that the air is moist. Relative humidity. The degree of moistness of the air is determined by a quantity called relative humidity. It is defined as the ratio of the mass of the water vapor actually present in the given volume of air to the mass of the water vapor required to saturate the same volume of the air at the same temperature. At dew point, relative humidity is 100%. If relative humidity exceeds 60%, we feel that air is moist. If it is below 60%, we feel that the air is dry. Example: on a clear day, white trails may be seen behind high-flying aircraft. The water vapor from engine condensed to form a cloud. If the surrounding air is moist, having more relative humidity, trails are long and takes long time to disperse. If the relative humidity is low, the trails are short or may not form at all. Units of heat. Heat is a form of energy like light or sound. Its CGS unit is calorie. Its MKS unit is kilocalorie. Its SI unit is joule, denoted by J. Calorie is the quantity of heat required to raise the temperature of 1 gram of water through 1 degree Celsius from 14.5 to 15.5 degrees Celsius. A kilocalorie is the quantity of heat required to raise the temperature of 1 kilogram of water through 1 degree from 14.5 to 15.5 degrees Celsius. Specific heat capacity. Specific heat capacity is defined as the quantity of heat energy required to raise the temperature of unit mass of the substance through 1 degree Celsius. It is usually denoted with the letter C. Its unit in CGS is calorie per gram degree Celsius. Its unit in MKS is kilocalorie per kilogram Celsius. Experiment of specific heat capacity with 3 solid spheres. For this experiment, take 3 solid spheres made with iron, copper and lead, each having the same mass. Heat them together in boiling water. After some time, remove them from boiling water and keep them on thick slab of paraffin wax immediately. The paraffin wax will melt, but we will notice that different spheres penetrate to different depths into the wax, and quantity of wax melted is different for different spheres. The sphere that gives out more heat will melt more wax and will penetrate deeper into the wax. Specific heat of iron is more than copper and lead. Hence, iron sphere will absorb more heat, copper will absorb less, and lead even lesser from boiling water. Iron sphere will give more heat to the slab, lead sphere will give least heat to the slab. This observation shows that the above 3 spheres have absorbed different quantity of heat from boiling water. This indicates that the sphere must possess some property which changes from material to material. This property is called specific heat capacity of a substance.